Great. Thank you very much. Thanks, Elizabeth, for the introduction and for the opportunity to speak, for the invitation. I'm incredibly excited to be a part of SMI 2021. I also want to give a big thanks to Ying and the Emory crew. This has been an incredible event, and I've really enjoyed every minute of it. So, well, except for the part where I'm talking, but that's normal. So thank you very much. I really appreciate that. I really appreciate that, everything that's gone into making this such a great success. So I wanted to start out with a bit of a shameless plug for our group at Penn. We call ourselves Pensive, or Penn Statistics and Imaging and Visualization Endeavor. We're a group of biostatisticians who focus on methodology and applications for understanding human health and improving human health through biomedical imaging. If you're interested in learning more about our group, please check out our website. And the motivation behind this shameless plug was that we're actually recruiting at all levels now. So please feel free to reach out to me if you're interested in learning more, or check out our website. I also wanted to give a big thank you to all the collaborators who've made this work possible. I'm going to give a shout out to particular folks who led the work that I'm describing as we go, but many thanks to the broader group that really made this work possible. And just as a sort of an overview of what I'm planning for the next 15 to 20 minutes, is I'd like to start with just a brief introduction to multiple sclerosis for anyone who may have missed the absolutely exceptional collaborative case studies yesterday on MS imaging. And then I'd like to talk sort of at a more course level about some problems and some opportunities that we see in the area of MS imaging. I don't have any formulas or any very rigorous descriptions of the methodology that I'm going to describe to you. So if you have particular questions, I'd love to talk more about those offline or in the discussion. I can also share the papers and details through that. So for those who may have missed yesterday's incredible session, multiple sclerosis is an immune-mediated disease of the central nervous system. Our best estimates of prevalence now are as high as 1 million Americans in the United States actually have multiple sclerosis, and MS is actually 3 times more prevalent in women than men. It also is associated with disability, which can be severe, and a reduction in expected lifespan. The hallmark of MS is the white matter lesion. These are lesions that occur in the brain and spinal cord, and reducing the incidence of these lesions is really a key goal, both in the management of disease, people who have multiple sclerosis, and also in the context of developing new therapeutics. So what you can see here, I hope this my cursor comes through here as well. If you can't see it, please let me know, because I'm going to point at things quite a bit in this talk. So what you can see here is an axial T2 weighted, an axial slice of a T2 weighted FLAIR image of someone who has MS. This is an image acquired at 3 Tesla on a Philips scanner at Johns Hopkins by Peter Calabresi's group. And in this particular way, we can look at the brain. You can see at the end of this big long arrow is a hyperintensity, or a bright white spot that exists in this image right next to the ventricle. Indeed, we can see paraventricularly there are actually several lesions, and we also see these lesions or hyperintensities in the deep white matter as well as next to the cortex. These regions of hyperintensity are known are the defining characteristic of white matter lesions, and the accumulation of these lesions is known to be bad, prognostically poor in terms of disability and worse outcomes. Now, when we scan people with multiple sclerosis, we don't just take one image. We often actually you almost always take multiple different kinds of images in the scanner. And these images, the axial views I'm showing you here, are about 1 millimeter thick. They look different slightly, and the lesions look different slightly on these different contrasts as well. So what you can see here are, again, that T2 weighted FLAIR contrast that you see in the upper right corner as well. And this is called a T2 weighted image. This is a proton density weighted image, and this is a T1 weighted image. Now, lesions show up differently on these various contrasts, especially on the T1 contrast compared to these other so-called T2 weighted contrasts. Lesions on the T1 weighted contrast are darker, and generally lesions that occur on the T1, fewer lesions occur on the T1 weighted contrast compared to the T2 weighted contrast. We'll talk a little bit more about that as well. We care very much about trying to study these lesions and measure these lesions because, as I mentioned, they're important in the context of patient management, and they're also important in the context of determining therapeutic effects in terms of interventions, as well as studying the underlying etiology behind multiple sclerosis. So I'd like to talk to you, again, at sort of a higher level view over the next 15 minutes about some work that our group has been doing and some opportunities that we see for being able to use statistics to better understand the natural history of this disease process, as well as the nature of these lesions. And I'll talk a little bit more about that in a few minutes. So generally, how do we find and count these lesions? Well, clinically, a radiologist will take a lesion and we'll take an image and just look at it and identify lesions visually. They'll report things like count of lesions. They'll report descriptions of locations of lesions. And then if there are changes in lesions over time in patients who are followed serially, they'll also make qualitative descriptions of the lesions that have changed, the lesions that are occurring over time. In the context of quantification for further research study and for more quantitative precision medicine therapeutic strategies, we need to do better than that. I should say we need to do more than that. And the goal then becomes, in the context of lesion detection, actually painting where lesions are. What you can see here are images. These are images acquired by Rob Bacci's group at the Brigham. And here is, again, a T2 weighted FLAIR image in which there are multiple paraventricular lesions, some deep white matter lesions as well. In order to be able to determine where these lesions are, the gold standard is actually to still have an expert color in where lesions are. So this is what you see here in the right panel. An expert's just painted where lesions are. And this is a very time-consuming and expensive technique, but it does allow us to be able to identify lesions in terms of their location across the brain. There are also countless automated techniques that have been developed for this task. Right now, as a field, I'd say we're pretty good at finding lesions using automated techniques. We're not actually great at it, but we're pretty good at it. This technique here called Mimosa was developed by Ali Belkursel, who was a doctoral student in our group, who's now at Genentech, who worked on the development of a T2 weighted and T1 weighted lesion detection method. This is that we call Mimosa, leveraging something called intermodal coupling analysis. This is something actually that Kristen Lynn described in her talk very nicely earlier today. But this is just a way to be able to extract additional features to be able to better understand what's happening in the brain of someone who has multiple sclerosis. And here's the output, I should say. Here is the output of that segmentation. I also mentioned that lesions don't look exactly the same on all different contrasts. This is a T1 weighted image from that same subject image in Boston. And you can see that actually fewer lesions show up as dark on T1 compared to those that are bright on T2. And identifying lesions that are dark on T1 is also of great interest because we know that lesions that are darker on T1 tend to have more axonal damage and more demyelination. And so it turns out that there are indeed automated techniques that are available, including Mimosa, to be able to determine where these lesions are as well. Another question that I alluded to in the description of clinical management of the disease, and one that's we believe is highly relevant, is the tracking of lesions over time. So this is done by this is work done by Elizabeth Sweeney and Chipran Kranichanu, a technique called Sublime that allows you to be able to integrate information across time points to be able to determine where lesions are. So for example, or I should say where lesions are changing. So for example, what you can see here in the top panel is a subject whose image at the NIH by Danny Reich's group, and in the red box here, you can see a lesion. 6 months later, I believe it's about 6 months later, you see the similar set of images acquired in this particular subject in which that lesion is grown. And determining where these changes are is of critical import because this is indicative of the fact that, or I should say this change here is indicative of the fact that this patient has active disease and could be switched, for example, to another therapy or might benefit from additional therapeutic interventions. And so Elizabeth developed a technique called Sublime, which works remarkably well, leveraging statistical normalization as well as a modeling step to be able to integrate information to be able, again, to determine where lesions change and where there are new lesions. So one might ask, are we done? And actually, believe it or not, oftentimes when we submit papers that study the nature of lesions or study additional characteristics of the disease and multiple sclerosis, reviewers will come back and say, MS, MRI is a solved problem. And we don't believe that's the case at all. Because what we can get from our current techniques are indeed a segmentation and delineation of where lesions are. And in the context of high temporal frequency longitudinal follow-up, we can also get changes over time, but we often rarely have that kind of high temporal frequency. So we're left And that's just because of cost. MRIs are really expensive and they're cumbersome in terms of acquisition with respect to logistics as well. So what we're left with is trying to understand disease processes based on a single cross-sectional segmentation. So this segmentation process takes an image like this, turns it into a map like this, and from there we can get a few different numbers. We can get, for example, lesion count. That's something that's used often in trials and in other aspects of MS research, and lesion volume, which is the total number of volume of lesions. But one might ask, is that enough? So to be able to address that question, I'd like to play a little game with you all. Let me figure out how I can see the chat. This will require slightly more. Okay, there we are. Okay, this requires technical sophistication that I lack. So, here we are. So here's a question. Based on this image, this is again a T2 weighted flare image, you can see that there are white spots. How many lesions do you all think are there? And if you've heard me ask this question before, you're disqualified. Okay, well, you're both disqualified. Excellent. Well, we have quite a range here, and I think that's actually an excellent point. Thank you. Thank you. Awesome. So I tend to agree. I tend to agree that, maybe I see around 4 lesions. Well, if I were to apply an automated technique for detecting lesions, this is what I'd get. I'd get 1 connected component. And the reason why is because actually this area of lesion or area of hyperintensity is connected in a lower plane. It's a U, and we're chopping off the top of the U. And so it looks like maybe there's 2 spots here, but it's all connected. There are some spots where the hyperintensity is all connected. So one might ask, is that true? And is that actually biologically informative? If you want to study lesions, does it make sense to study this big U shape? Well, we know that lesions tend to be ovoid or round-ish, ellipsoid in their shape. They don't tend to be this U shape. So what's going on here? Well, luckily, this particular image was acquired as part of a natural history study done at the NAIMS, in which people were imaged monthly over a period of years, actually decades, some of them. And this is what happened in terms of the natural history. So this baseline is today, but 8 months before baseline, there are actually 2 separate lesions that were disconnected in space. A month later, a 3rd lesion appeared, and then 2 months after that, a 4th lesion occurred that connected them all in space. So one might ask, can we try to recapitulate what we're looking at here based on just this image without having to try to scan people every month, which is just clinically, and in most cases, even in research, infeasible due to cost? Well, Jordan Dworkin has been working on this problem and actually has a solution that I'd like to talk to you about for a few minutes. So his idea was to take, for example, an image like this, do automated segmentation, and then not just take the 0-1 description of where you see lesion and where you don't, but to model the shape and the texture of this lesion. In particular, lesion segmentation doesn't give us just 0 or 1. Oftentimes, it will give us an estimated probability at every location. Do we see lesion? 80% yes, 20% yes, and so on. And so Jordan's idea was to be able to study the texture of this pattern. So this is, again, actually on the top right here, you have the output of that Mimosa algorithm I was describing. But from the vast majority of lesion segmentation techniques, you can come up with such a map and then ask, how many, for example, peaks do I see in lesional intensity across this map? And so using basically a peak detection algorithm that he implemented, he was able to determine centers of lesions. And then based on those centers, he could do the same thing that people do in standard practice in the context of lesions or of segmenting different things in an image, and just count the number of those centers. So here's an example of how that works in the context of this image. Going back to our original example, indeed, the answer that he found was also 4. So how does this do in a larger set of data? Luckily, we did have data from 60 people, again, scanned at the NIH approximately monthly over a period of up to 5 years. And we use that technique Sublime to be able to look over time and determine where we see lesions. And then we compare this high temporal frequency, extremely expensive, unusual imaging to be able to, the results from that unusual imaging to be able to look at how lesions formed over time and count carefully how lesions formed over time, and thus be able to then determine sort of a gold standard count of number of lesions over time and compare that with Jordan's count. And these are the results. So you can see here in the blue dots, we have the comparisons of the assessments using Jordan's count. And in the red dots, you have actually the sort of standard connected component analysis count. And clearly there's a great deal of deviation here with an underestimation of number of lesions in the cases where more lesions are present, which makes sense because if you've got more white spots in an image, it's more likely you'll have more connected lesions and what we call conformal lesions. In the interest of time, I won't describe all of the clinical implications and what we think might be going on here in terms of these associations, but suffice it to say that actually we found that the associations between clinical phenotypes and Jordan's count was actually more informative than we got from standard counts. The next thing I wanted to talk to you about was the problem about lesions not all being the same. So I described to you briefly the difference between standard T2 weighted lesion counts or standard T2 weighted lesion volumetrics, and then the assessments of these black holes, these lesions that show up as dark on T1 weighted imaging. But with new MRI, we can actually, in advanced MRI, we can tell a lot more about lesions than just what they look like on T1 and T2 weighted imaging. And a key application of this, or a key problem that motivates the analysis and the development of these kinds of tools, relates to diagnosis. So Andy Solomon's a close collaborator of ours who is up at University of Vermont, and he's actually made a career describing the problem of misdiagnosis of multiple sclerosis. And there are many different sort of assessments of how often MS is misdiagnosed, but the number the range, I should say, of prevalence of misdiagnosis of multiple sclerosis by many estimates are in the 1/5 to 1/3 range. It was 4 Chipperon. Sorry, I should have said that. If we were in person, then I could have given a prize to everyone who guessed 4. But sadly, we'll have to wait for next year. Sorry. So in the context of diagnosis, misdiagnosis is really important to be able to find out not just whether people have lesions and how many lesions they have, but also the nature of their lesions. Are their lesions actually MS lesions, or could they be due to something else? And so I'm just going to check on time. Okay. And so another very important question is, are there ways to be able to quantify lesions that indeed are more likely to be MS lesions compared to non-MS lesions? And that's where a new kind of imaging called central vein imaging has been actually very helpful and is increasingly being advocated for in the context of clinical practice. What you can see here, and I think I'll probably end with this picture, is a figure from Pascal Satti's group in the NAIMS cooperative looking at differences between people who have multiple sclerosis and the lesions of people who have multiple sclerosis and MS mimics. So what you can see in the top row are people who have MS, and the bottom row are people who don't have MS and whose lesions look pretty similar on standard FLAIR and T1 weighted imaging. But on this new T2 star or FLAIR star imaging, you can see features that actually describe the central vein that we know goes through MS lesions. And trying to quantify these, I think, is also a really interesting and promising problem that I would love to talk more about in the discussion period if there's time. I think I'll end there, but thank you very much for indulging with the game and so on. And I look forward to the discussion.
Next up, we have Julia Wrobel. She's going to be talking about intensity warping for multisite MRI harmonization. So Julia, if you want to share your screen, great. Oh, Julia, I think you're muted.
Sorry about that. Hold on just a second and I'll reshare. My computer's freezing a bit. Okay. So thanks for having me, Elizabeth. I'm really excited. I'm excited for next year when we can be in person as well. But so for those of you who don't know me, I am an assistant professor in the Department of Biostatistics and Informatics at the Colorado School of Public Health. And I'm going to talk about intensity warping for multi-site MRI harmonization. So most of you are familiar with structural magnetic resonance imaging data, but for those of you who aren't, you get images that are 3D images comprised of voxels. Voxels are 3D pixels, and each voxel contains a grayscale intensity value. And here's a sort of 2D slice of what that would look like. Often in studies, multi-site imaging is common. You get people scanned in a machine like this. I actually had my first ever MRI last week, so I now have a personal understanding of what that feels like. It's pretty claustrophobic in there, but it was interesting to see how the data was collected sort of personally, since I like analyzing this type of data. But in a lot of these studies, you're going to collect MRI images at different scanners and at different sites, potentially across the country. And imaging at different sites can induce unwanted scanner effects. And so there are a couple sources of variability in MRI studies that are unwanted non-biological technical variability. One of those is the scanner effects I just mentioned, and the other are what we call intensity unit effects. And intensity unit effects are due to the fact that when you collect an MRI scan, the voxel intensities are unitless. They have arbitrary voxel intensities. And so when you get a scan from one day to another, even on the same machine, the same voxel can take on a different value. And so there are a couple of methods out there, some of which Taki discussed already, that deal with intensity normalization. Popular ones are histogram matching and white stripe, one of Taki's methods, which normalizes based on normal appearing white matter in the brain. And intensity unit effects are like always there. No matter what scanner you're using, you're going to have intensity unit effects due to the arbitrary voxel intensities. Scanner effects, however, are present when you have studies collecting data on multiple scanners or multiple sites. And these are due to across scanner or across site variability due to difference in machinery. And there are a couple intensity harmonization methods as well. I'm going to talk about one here too. One of the popular ones is combat, which harmonizes specific brain regions, but we want to harmonize the whole brain. So just to motivate a little bit of why scanner effects can be bad, I have some images here from the NAIMS study, which is a multiple sclerosis study that Taki mentioned, where the same subject was scanned 2 times each at 7 different sites across the country. And this subject has multiple sclerosis, but it's stable, and the scans were collected close together in time so that lesions should not be changing. However, what you see is that on this NIH study on the left, you have some lesions appearing in this yellow box that exist on this scan, but don't exist on the scan that was collected at Ohio State. And these are due to scanner effects. And so looking a little bit more into that NAIMS data, I've now plotted the intensity distributions for scans from 3 of the different sites, 2 from the UCSF site, 2 from Ohio, and 2 from the NIH. And you can see both the intensity unit effects and the scanner effects present here. At the NIH, the 2 scans are rather similar. There aren't a lot of intensity unit effects, whereas at the UCSF site, the 2 scans are quite different. Scan 1 just has a lower overall intensity value that's less stretched out than scan 2. So there are larger degrees of intensity unit effects here. But the largest degree of variability in these distributions of intensities is coming from across site variability, where the UCSF scans are really quite different in their distribution of intensity values than the scans that were collected at the NIH. So one of the goals of intensity harmonization is to remove those scanner effects in scans that were collected at different sites, which can help you increase the experimental power in downstream analysis, and also just make sure that when you have a study, when scans are collected at different sites, you can really have confidence that you're comparing things that are similar. And the approach that we're going to take is to transform the data so that all images come from the same intensity distribution. And this approach leverages multiple scans collected on the same subject and scanner to separate out biological and technical effects within that subject. So another important data set that was used to design this harmonization method comes from the TRIO to PRISMA study. And in this study, 10 healthy subjects were scanned each on 2 different machines, a TRIO machine and a PRISMA machine. These are 2 different scanners. And these scans were collected at the University of Pennsylvania. All scans were collected between 2 and 11 days apart, so that brain structure is not expected to change in that time period. You can see from the plots of the distributions here that there are some systematic differences seen between the 2 scanners across the subjects. So all of the subjects' scans on the PRISMA machine are in purple, and all of the scans on the TRIO machine are in green here. And one subject is bolded, and you can see they exhibit a similar pattern from the rest, where the PRISMA scan tends to be at lower intensity values than the TRIO scan across these subjects. And so what our goal is to use a technique from functional data analysis called registration to remove that scanner variability by aligning intensity distributions. And the way that this sort of works is you take a set of unharmonized distributions. I have a toy example here on the left, one subject highlighted in red. And then you transform the intensity domain in a monotonic way by stretching and compressing that intensity domain for each of the different distributions so that the distributions are aligned, which you see on the right here. And the way and I'm going to go through a couple slides just to show you how we do that in the context of harmonization for these images. And the technique that we've come up with is called mica, which stands for multisite intensity harmonization by CDF alignment. On a sort of toy level, you start with 2 images from the same subject who have different intensity distributions for those images because they were collected on different scanners. You then transform those images into their CDFs, their distribution functions. You calculate the transformation to align those CDFs, and then you use that transformation and apply it to to generate new images that are now harmonized. So in that first step, you take those images and you calculate the empirical CDF based on the intensity values. And on the right-hand side here, we have a plot that shows the CDFs for 2 images from the TRIO to PRISMA data set. This is one subject, and you have the TRIO image in orange and the PRISMA image in green here. Then in the next step, you map the TRIO scan onto the PRISMA scan. And in this case, we choose to map TRIO onto PRISMA because PRISMA is a higher resolution, newer machine, so it represents sort of the better data. And so we calculate a transformation that maps the CDF of TRIO onto PRISMA. And then finally, we take that transformation. An example of what transformation like that could look like is shown here. Hold on just a second. Where say I start with an intensity value in my image that I want to harmonize of 4,242, and the transformation defines a new intensity value of say 7,363. And we apply that transformation to every voxel in the image that we want to harmonize. So the voxels that took on a value of 4,242 in the old image and the harmonized image now have a new voxel intensity value, the 7,363. That's how we apply the warping function to the data to generate harmonized images. And so this is sort of the best case scenario. In the data set I'm talking about for TRIO to PRISMA, all subjects were measured on all of the different scanners. So all subjects were measured on both scanners, so we can learn the transformation between the scanners for every single subject. And then we can assess how similar are these transformations across subjects. And ideally, if these transformations are similar, then we don't need rescan data from all subjects in order to get good results for our harmonization. We can use a subset of those subjects to calculate an average transformation that will then be applicable to the rest of the subjects in the data set and will remove some of those scanner effects. Applying our technique to the NAIMS data, you can see this is one subject who was again scanned twice at 7 sites across the United States. And we harmonized his data using this technique. And you can see in the beginning, we had the same distribution functions that I showed you, the same density functions that I showed you that were not well aligned. And after applying our transformation, as well as intensity harmonization, the scans are well aligned. And similarly, after applying this to the Trio to Prisma data, after alignment, the PDFs are more comparable, not only across the whole brain, which is shown on the first row here, where you have the transform both before applying our method and after. Now the scans are all more on the same domain, but this similarity holds true in the white matter and the gray matter as well. Even though the transformation was only applied to the whole brain, we didn't do anything specifically to target the white matter or the gray matter. It still makes those areas more comparable. And finally, mica preserved original biological features in the brain a lot better than histogram matching, which is an intensity normalization technique that is often used for harmonization as well. You can see a mica scan here looks very much similar to the raw scan, but the histogram matching has some weird artifacts going on in this area of the brain. And so after harmonization, the lesion volume is more similar as well. I'm going to skip this slide and maybe talk about it in discussion because we have some updated results that are a little bit nicer. Because I want to talk a little bit in the next few minutes about using mica in practical settings. I mentioned that the Trio to Prisma is sort of the best case scenario where you have all subjects measured at all different sites, which for most studies isn't going to be the data that you have. So I want to talk about using this approach when you have data sets where not everybody was measured at all sites. So mica is intended, so practically speaking, mica is intended to reduce scanner effects, but not intensity unit effects. And so we recommend pairing it with a normalization method to reduce intensity unit effects. And we recommend white stripe for that because I worked with Taki on this, but also because it gives you a more interpretable voxel intensity value. But then, and most multi-site studies have scan rescan data for only a handful of subjects at best. So some of this shows that we really need to collect more to get a good baseline for what scanner effects looks like. And we tried crossed-out validation on the Trio to Prisma data to get a sense of how well this would work in practice in future studies. And the way that cross-validation was designed, we call it leave one, scan out cross-validation, is for one subject, you remove their Prisma scan, then you estimate the Trio to Prisma warping functions for the other 9 subjects in the data set, and then you compute a pointwise mean of each of those warping functions. And then you apply that warping to the held out subject. So their data was not used to calculate the transformation to remove the scanner effects. And then you repeat that for each of the 10 subjects to get a sort of a warping function for the held out subject. And using this leave one scan out approach, for harmonization, which is more realistic, we still see sort of better harmonization than we did before. So the scans are more comparable, they're coming from more similar distributions. So just some conclusions and future directions. Scanner effects and intensity unit effects are distinct sources of unwanted technical variability in MRI data. They use both normalization and harmonization methods. Larger studies are needed to better understand differences across scanners, however. Like, how can we better incorporate covariates to estimate better transformations between scanners, for example? Maybe scanner effects are more take a certain sort of shape for one age and different for another. So in being able to incorporate covariates into how we calculate those transformations could potentially help. And then another conclusion is that all multi-site studies are beginning to do this and really should obtain baseline measurement of scanner variability by sending around a subset of subjects to all of the scanners in the study. All right, thanks a lot for listening. My contact information is here. I came from Columbia. I graduated from my PhD from there about 2 years ago, and some of this work was done with my advisor there, Jeff Goldsmith. And I also thank the Pensive group where I worked with Taki and Melissa in his lab, and it was a lot of fun. So, and I'll take questions after the talk.
So our last talk today is from Carolyn Lou from University of Pennsylvania. She's going to be talking about towards an automatic detection method of chronic active lesions and multiple sclerosis. So I'll hand it over to Carolyn.
Great, thanks, Elizabeth. 1 second. Okay. Does this look right to everyone? We're just seeing the slides. Awesome. Okay, so I'm Carolyn. I'm currently a graduate student at the University of Pennsylvania, working with Dr. Taki Shinohara in the Pensive group. And I'm delighted to be speaking here today alongside so many brilliant people at this wonderful conference. So many thanks to Elizabeth for the invitation. So briefly, this is a little bit of a rehash from earlier, but multiple sclerosis is a chronic inflammatory disease of the central nervous system, characterized by demyelination of nerve fibers in the brain, optic nerves, and spinal cord. For patients with multiple sclerosis, this demyelination can result in symptoms that include muscle weakness, fatigue, or cognitive impairment. And current treatments aim to reduce inflammatory activity and slow clinical progression, but as of right now, there is still no known cure. In the brain, multiple sclerosis is diagnosed and monitored with structural magnetic resonance imaging, or MRI, through the quantification of white matter lesions, which Taki talked about a little bit earlier. So common measures for the quantification of white matter lesions include total lesion volume, lesion count, and on some level, also the age of a lesion. And in fact, some of these measures are included in the McDonald criteria for diagnosing multiple sclerosis. On the right here, we can see some examples of lesions in the brain. And as was alluded to before, on different imaging contrast, lesions can appear very differently, thereby motivating work with multi-modal analyses. So something that has been observed is this disconnect between these common measures that I just mentioned and a patient's lived experience, in that an increased lesion load does not always correspond to a higher EDSS, and conversely, a patient with a low lesion load may experience more severe symptoms. This phenomenon is called the clinical radiological paradox, and this paradox is increasingly understood to be in part due to the heterogeneity within MS lesions themselves. So in this talk, I'm going to focus on one particular subtype of white matter lesion called the chronic active lesion, which was also discussed in detail yesterday at yesterday's collaborative case study session. So the chronic active lesions are a subset of white matter lesions that have chronic inflammation at the lesion edge. On a T2 star phase contrast, specifically, they manifest with a hypointense rim. And what the T2 star phase image is picking up here is actually iron deposits left by iron-laden macrophages that are thought to be associated with this continuous inflammation at the edge of the lesion. For the purposes of this talk, I will be referring to these lesions as paramagnetic rim lesions, or pearls. So the presence of pearls in a patient has been shown to be associated with greater disease burden, and has also recently been shown to be visible on 3T MRI. This motivates our work, developing an automated method for detecting these lesions for increased study of these lesions in the clinic. So currently, identification of pearls is largely performed manually, which can be very time consuming. And actually something that poses a challenge with manual identification and also automated identification schemes is that the quantification of paramagnetic rim can be difficult due to its varied presentation. Even in this figure right here, we can see, for example, lesions where on some of these lesions, the hypointense rim is very clear on all sides of the lesion, but for some of them, the rim only appears to be visible in certain spots, and for some of them, the rim is less hypointense than it manifests in other lesions. So to study this, we use data from 19 patients with multiple sclerosis, for each of whom we collected 3 T1 flare and T2 star magnitude and T2 star phase MRI images. Here, we also specifically selected cases of MS known to have at least one paramagnetic rim lesion. Pearls were identified manually using both the T2 star magnitude and the phase as a lesion with both a hypointense signal on the periphery of the lesion, as well as being hyper or iso-intense in the inner portion. So broadly, our method follows 4 steps. The first of which is image pre-processing. We then followed that with an automated lesion segmentation tool called Mimosa, which was developed by an alumni of PennCIF. We followed that up with an automated lesion identification scheme, through which we use a lesion center detection method developed by another former alumni of PennCIF, and we followed that with a little nearest neighbor lesion labeling scheme. After we automatically identify all of our candidate lesions, we then employ first order radiomic feature extraction to use those as features in a random forest classification model from which we classify our lesions as pearls or not. So for lesion segmentation, we employed a method called Mimosa, which is a multimodal method that extracts localized intermodal coupling features from input contrasts. These intermodal coupling features, which you may have heard about earlier today from Kristen Lin, are derived from locally weighted linear regressions, which are then used as features in a classification model used to predict voxel-wise lesion probability. From those lesion maps, lesion probability maps, we then use Jordan-Dworkin's lesion center detection method, which identifies the centers of distinct lesions by exploiting the second order moments of the voxel-wise lesion probability map. We can see on this figure that this mass in the center is labeled a single lesion by a connected components analysis, but after employment of the center detection method, we can see that the one mass is split up into 4 distinct lesions, which more closely reflects what a manual rater might label this mass. Once we find these lesion centers, what we then do is simply take the remaining unlabeled voxels and assign them to a lesion according to which center is closest, simply by Euclidean distance. So once we complete identification of all of our lesions, we use first order radiomics to characterize the lesions along a number of different features. So first order radiomic features are features that specifically describe the distribution of voxel intensities within a given region of interest. Here we extracted features like the mean, median, and the variance. So here we have 2 example lesions, the top one of which is not a pearl and the bottom of which is a pearl. And we can see that when we plot the distribution of the intensities, we can see that the distribution may actually differ between these two lesion types. And with these examples in particular, we can see that the two, and between these two example lesions, the lesion that is a pearl may exhibit on average lower intensities than its non-pearl counterpart. So here are some more example lesions at each stage of our processing pipeline. Each column corresponds to a different step in our method, and each row corresponds to a different lesion with a different classification result. So the first row exhibits a lesion where our manual rater rated it as a pearl, and our classification algorithm also did so. Something that I want to note here is a little technical detail that if you can see in row B for our false positive that our lesion segmentation map does not actually seem to cover the entirety of the lesion itself. And this is in fact something that we had thought about so like ways to deal with it. So this map that I'm showing here is actually a dilated version of the segmentation map that we derived from Mimosa. And this resulted in inclusion of more of the lesional area. What we can see though is that with this dilation in our row C with this false negative is that this dilation may have unintentionally diluted the signal from the rim and resulted in an incorrect classification result. Along those lines, in row E, we have an example of confluent lesions, which I touched on earlier. But because this set of confluent lesions was called a single lesion, again, even though for one of the confluent lesions, we see a fairly clear paramagnetic rim signal, this dilation or the inclusion of both of these lesions as a single region may have resulted in an incorrect classification result. So in total, we found 877 lesions across our 19 subjects, 13% of which were pearls. We found an average of 46 lesions per subject and an average of 6 pearls per subject. And to evaluate the performance of our automated lesion identification scheme, what we did was, because we didn't have a gold standard count of the number of lesions in each subject, we simply compared the number of pearls that were identified manually to the number of pearls that were automatically identified. And what you can see here is that those two counts are highly correlated. To evaluate the performance of our classification, we trained a Pearl classification algorithm on using a train test scheme from which we saw an AUC of 0.8. The corresponding ROC curve is plotted here. To assess the variability of that AUC as well as other performance measures, we conducted 1,000 resampling iterations with the same test using a train test split. So if we want to dive a little bit deeper into our classification results, we can see here that our high performance can be, maybe it's largely driven by the classification model's ability to predict, to accurately predict rim negative lesions. And this is reflected in our sensitivity and our specificity as well, where you can see that our specificity and our negative predictive value are comparatively high, whereas the corresponding sensitivity and positive predictive value are comparatively modest. Across these 1,000 resampling iterations, we have like a little confidence interval here. So we can see also that the variability for sensitivity and positive predictive value are also higher than their counterparts. Something to note is that, again, earlier I mentioned that confluent lesions were present in our data set despite us using a lesion-centered detection method in order to try to mitigate that. But to explore the impact of confluent lesions, we did a simple analysis where we said that if a connected components analysis said that one mass was a single lesion, but our center detection method said that there were multiple, we simply called that whole mass a confluence of lesions and excluded those from the analysis. What we can see with the contingency table is that this ended up removing most of our lesions. But despite that, after the exclusion of all of these confluent lesions, we can see that across the board, our performance measures actually improved. So now if we want to dive a little bit deeper into the classification model itself, what we can see here is that entropy, uniformity, and energy were the three measures that were the most important for determining whether or not a lesion was a pearl. With these in subfigure B, what we can see with these box plots is that the distributions of entropy, uniformity, and energy differ between pearls and non-pearls. In particular, for entropy and uniformity, we can see that pearls tended to have lower values of each of these measures, as well as and had lower variability. In contrast, energy was higher for pearls than non-pearls on average, with non-pearls potentially exhibiting a more heavy tail. So to break this down a little bit, entropy is a measure that is typically thought of as quantifying the variability of intensities. Here, something to note is that because of the way that we defined entropy, pearls ended up having lower entropy than their non-pearl counterparts. And this could be due to, in part, because here, because we didn't discretize our intensities, entropy served essentially as a proxy for lesion size. So here, because as entropy, as lesion size increases, entropy then decreases. So here our results actually suggest that pearls tend to be larger than their non-pearl counterparts. I think uniformity, the results make intuitive sense, and energy here is higher for pearls and non-pearls due to in our T2 star phase contrast, hypointensities manifest as more extreme negative values. So once squared, those result in higher energy values. So today I've discussed an automated method that developed for the identification and classification of paramagnetic rim lesions. Some benefits of automated identification methods in general is that they can ease the burden of manual segmentation and mitigate the impact of inter and intra-rater reliability. Something to consider for the future is that with our current method, there was a comparatively modest sensitivity, and also something to consider is the impact of confluent lesions. So I'd like to acknowledge some people who helped me work on this project, and here are some key references. I'm happy to take questions.